Welcome back to our Cloud Computing and Big Data Lecture 2 on machine learning models in clouds. We have the second part with machine learning in clouds. So in the first part, I hope you got basically the essence of machine learning with a simple learning model, linear learning models, linear in weights. So that means it's one of the very simplest learning models you can actually have. But then, of course, it shows you that you can actually do the job of binary classification if the data is linearly separable. So that was a very, let's say, strong assumption that in practice you rarely have, to be honest, but it still is a very good introductory data set to understand machine learning, the different phases you have, where hopefully the crisp DM shows you a little bit always this perspective on the broader parts, right? Machine learning is not throwing an algorithm to data and execute. That's not what machine learning is. It is a whole process of starting what I want to do, business understanding. It's an idea of looking at the data, data understanding, data exploration. What can I do with the data to make this business understanding, data understanding to do the job? So how can I do binary classification? Then I have to do some data preparation. If you have listened carefully, you have seen I changed sometimes the iris setosa and iris virginica from text into +1 and -1 for mathematical convenience and also to learn properly with the learning models in a mathematical fashion. This could be considered as a data preparation. And when I have done all these different steps and the data is basically ready for the algorithm, then the machine learning comes into play. Then we learn the weights which are necessary for the model to really express the data we have, to really learn from the data we have in order to create a machine learning model. And then, of course, we want to evaluate it. We left that a little bit out in the first part of the lecture, and we'll come back to this in many different forms in this part of the lecture now. But in the end, the important message for you to take away is really machine learning is a process. If you're not satisfied in the evaluation with the machine learning model you have, like the, let's say, linear regression was not very nice, or the linear classification was not really nice, or the logistic regression was not really nice, and you hop. You go to the support vector machines, you go to neural networks, and then the whole process starts maybe a little bit partly again, because you need probably to prepare the data differently. And these are things we will do in the next couple of lectures to really show you again and again machine learning is a process. And of course, a machine learning course will give you much more insights than I can possibly do in this high-level cloud computing course. But the CRISP-DM phases that we will also look in the second part here now will give you the picture how it practically works when you have, let's say, a real world scenario. Now, in the second part, we want to combine now what we learned a little bit in the linear learning models now with real clouds and cloud providers. Also here we do a, let's say, very moderate introduction. We use also the Google Colaboratory, a little bit Google Cloud part, which is actually accessible for you to play around, which is one of the ideas so that you can also do it at home, play around with it. And of course, it will be part of our assignment 1 as well. So hence we're learning here a little bit already things which you should apply in assignment 1, which comes out probably just next week. And we start here by revealing a little bit some examples of, typical binary application problems and, to think about that these data sets are also existing in the cloud so you can make use of them. Here it's an example of, again, a binary food inspection that is now different from, this flower aspects. That's what I want to convey with it. So we can now use these methods that we learned, this binary classification, and put that to many different application problems. And one of it is here that you would have maybe restaurants. Here's the idea of city of Chicago, where they are basically, people checking these restaurants. They have a long, let's say, description of the restaurant, what is good, what is bad. They call that a food inspection process. And there's a report coming out of that. And the idea is, can we use this food inspection report to say, basically, from all these different restaurants, to see basically if a new restaurant based on all of these different aspects then will pass or fail the inspection, right? So this is another idea of pass and fail, saying +1, -1. It's a 2-class classification problem. So basically relatively trivial, but still kind of basic machine learning idea to really learn it well. You can understand that basically based on all of this text coming from some food inspector, there's probably not a really mathematical formula, right? There's no precise formula that says now, okay, KFC in Chicago at some point in time here and there, there's a mathematical formula. You have no chance of passing the food, the kind of food inspection, right? And so the violations here, of course, are basically encoded somehow into text. There's no mathematical formula. Now that's our process we can do with machine learning to put this a little bit into perspective. And of course, data exists. Here's the idea of the city of Chicago, for instance. Just an example of the application that is also around in clouds where you can get the data from. And you apply the same mechanisms. Now, what you would do is then doing a stepwise approach, like, for instance, using MS Azure HDInsight. We will talk more about HDInsight also in the next part, in lecture 3. We cannot integrate all of that in one lecture, it would be too much. Hence, we have a whole cloud computing course to come to. But you can there create something called a Spark cluster, usually because your laptop is too slow, you have memory problems, you cannot get the whole data in. And basically, this is the idea now, working again with big data, obviously. And then you have the stepwise approach we already were introducing in one of the earlier lectures. Usually you would have some form of a subscription in cloud to check. Is it a pay-per-use model? How it really works. So here you have to have basically HDInsight subscription. And once you have this, you can deploy a so-called Spark cluster in this HDInsight environment based on a, let's say, pre-configured template system based on MS Azure. And this HDInsight captures lots of open source tools. There's Apache Spark, there's Apache Hadoop, the Hadoop distributed file system. Now, the beauty is that you can usually access this kind of Spark cluster, this data analytics cluster, with a PySpark kernel in the Jupyter notebook, right? So you will be still able to, let's say, just implement in Python relatively high level in the Jupyter notebook, but by having a powerful big data analytics structure underneath. And that is what lecture 3 will entail. So we will look under hood, what we do here in lecture 2, and see what does the Apache Spark cluster really brings us compared to maybe Anaconda or Jupyter on your own laptop, right, with the scikit-learn and so on. Once you have done this, this is Jupyter Notebook, you connect the PySpark kernel, which is given to you by the cloud infrastructure. You create a so-called Spark session, which activates a cluster setup. And then, of course, the same steps from the CRISP a little bit will come into play. Now we will look, do we have access to the application datasets? Let's say the food violations. Do we have, let's say, a view on the data? So how we can inspect the data? What is the, let's say, features in the data? For this, we do data analysis, visualization, and then we can start the real modeling after that, right? So how we come to a machine learning model, how we come to a two-class classification problem like we had in the flowers. But with food violations, it would be the same way. You have new text of a new restaurant with violations. Will it pass or fail? Based on the different classes we had basically before of many different food violations from pass and fail restaurants. And this is just beautiful how that works. Of course, take away the message that usually the subscription is loaded. It could be 20 euro per month for such a subscription. It will not really entail what are the lower level resources. Do you have high memory resources and it will cost more? Things which are not obvious to you, but which we will talk about in lecture 3. Obviously, below for getting HDInsight, you have to pay a price for it. But you can do very nice machine learning model inside the cloud there on the Spark cluster, especially if you think away that you can just do it from your laptop. You swipe a credit card, nothing more. For a company that otherwise would have to create a cluster in-house, on-premise, as we say, right, in the cellar somewhere, cooled down, having 1 or 2 experts which install all the stuff, right, which is loaded. There's a real big effort going into getting the right versions of all the different Apache tools together to make it work. There are different open source tools that really have accelerated paces here and there in developments, different versions coming out, being incompatible with other versions, and then your whole cloud setup breaks. So the beauty here, if you pay it, so to speak, from Amazon, from Microsoft, no matter where you go, you have usually a streamlined set of versions. That's where you pay for. And of course, then the scalability of the resources instead of on-premise, where you just buy a couple of core machines and then realize, oh, that's too little. And then you buy more. And then at the end of the year, you realize, well, we bought too much, but we have to sell it again. So all this up and down, this elastic behavior we talked about in the cloud, of course, is here beautifully given. You can easily add resources. We call that Spark worker nodes. We will materialize this in the next section, and do lots of different machine learning models. And of course, that means also in the CRISP-DM process, as I meant, we evaluate the model, we revise the model. We maybe do other ideas of parameters, we do maybe other features into the gate. As I said, machine learning is a process, which should also be, again, coming up in this part of the lecture today, right? So here's a concrete other example, which is, I think, easy to follow. So if you think about bank clients, and this is something what you maybe also have to do a little bit in your assignment, so listen carefully. Here in the bank clients term deposit idea, you have essentially someone calls you from the bank and want to know, do you want to do a term, deposit? Yes or no? And of course, the bank has many different customers. And apparently, of course, it depends what job they have, what personality they have. So lots of data exists. In our example, this comes from Kaggle. It's a very known data set. But Kaggle is an interesting platform in general. If you want to look a little bit around, I would say it is useful to look at this. It's usually a bit massaged already towards machine learning. So it's easier to use. Let's say less of wrong values, missing values, etc., noise, and so on. Kaggle has usually interesting data sets to play on directly, similar like the UCI machine learning repository. In real life, this is not really always the case. We will see in lecture 11 and plus in the later parts of the course how that really is if you have real application data sets, maybe from retail or so. But coming back to our examples, we believe that there's a pattern, right? So they are previous bank customers, bank clients, and they probably, have said yes or no to a bank deposit. And we can derive this from all the different spending habits, the idea of, how the kind of personal aspects, so age and, job and so on, will influence this decision. But in the end, we're interested in the binary decision. So saying binary in terms of yes or no, do they want to do a bank term, kind of deposit or not? Again, number 2 is to be checked. Is there a mathematical formula? And you would say, well, not out of the heart, not analyzing, let's say, all of these different factors like age, like job, like whatever, where they live and so on, these customers. Hence, we have a typical binary classification problem, no mathematical formula, but the beauty is we have data. And this is what we will make use of by using the same stepwise approach, of course. And here, have the beauty of clouds. You're not sticking to one HDInsight, for instance, in MS Azure or to AWS. They have a very similar package, and Google Cloud has the same, was called CloudProc. Basically, they're all having these kind of ideas of having this Apache Spark clusters we will reveal in the next lecture. But also the Google Colaboratory, you know that a little bit. I think I already asked you in one of the earlier lectures who knows about the Colaboratory. This is a very nice way of Google access to a cloud service. Again, you would follow the same steps. You basically go to your browser, you go to the Colaboratory because probably your laptop is not going to make it. So you have a subscription model basically there. Of course, it's free here, generally in Colab, but you can have a small pay actually, and then you get a little bit more resources, more stable. But it shows you nicely that this kind of idea is very similar. You have a Jupyter sort of notebook in this Google Colab environment. And also there you can deploy a Spark cluster in the Google Colab. Basically, we will see what that really means in later lectures, because of course the Google Colab is not that scalable than the MS Azure environment if you put lots of worker nodes to it. So we have there to do a little bit of trick. But it's still the same look and feel, with Jupyter notebooks by using PySpark and so on inside this. We do the same way of saying create and use Spark sessions that they get access to the cluster environment, or to the cloud environment here, I should say more precisely, and do my visualization, inspecting the data, exploring the data, starting then with the modeling, and do this in a way of using Spark, right? And this is an application, of course, of data analytics package. We will learn more in lecture 3, and just today a little bit with examples, just to get you a bit warmed up what machine learning entails, what steps it entails, and so on. And then once you have, of course, done the model, you do again the evaluation and refinement. So you see the stepwise approach of using clouds for machine learning is more or less always similar. The only question is, what data do you have, which model you pick, and of course, which subscription you go. So which cloud provider is basically the best suited for it. It depends a little bit what modeling you want to do. We'll also learn later, the environment matters as well. Do you want to do the open source way in terms of these Apache stacks, or you maybe want to do something very sophisticated for AWS SageMaker, for instance? But then you go there and pay the price, right? You have to subscribe to the kind of payment models that these services entail, and then you pay a lot of money here and there. Usually the cloud vendors kind of hook you, if I may take this word, in giving you some free resources in the beginning. But then if you want to use it in production, let's say a company doing inference and training of data on a regular basis, then you quickly, have some credits to pay. And this will come again in another part of the lecture. So let us reveal a little bit how go through all these steps. And this is the idea today, that you learn these steps now a little bit in a concrete example, really, which is a trivial example. But of course, here the idea is to learn these steps also maybe in context of the CRISP DM, so that you see the machine learning process is kind of also part of this process. Step one, very obvious, you have to get the cloud environment right. Here as the example, you go to colabresearchgoogle.com. Basically, it's very open. Usually, however, if you want to connect it to data on your Google storage, you really need to have a Google account to make it really properly used, right? That's the only real requirement you would have. A Google account is, so to speak, more or less mandatory to use as cloud infrastructure here, especially because it takes these scripts that you create, these kind of Colab, Jupyter notebooks, and store them also in your Google Drive. And as such, it is personalized. And as such, you need your subscription or basically the account there. So then, of course, deploy and install a Spark cluster in Google Colab is something which is a little bit interesting. Firstly, because, of course, Google Colab is giving us a very nice cloud environment, but still not the very big data analytics cluster. It mimics a little bit, so to speak, the large cluster. And we can install these packages just to make use of the software of Apache Spark here in that regard. The scalability, we have to talk then in the next lecture about how we really with worker nodes go across many different nodes. But the Google Colab is a good start for you always to play around because it's open and free. You can, have the different examples already prepared. So I encourage you to go there, find some other notebooks and play with it. We will do this partly in assignment 1, of course, as well. So here you see, just to get a different, let's say, way of a JDK, of a sort of last, update on this. There's a kind of apt-get install, which is to say a specific command that enables us to go to the Unix level here and install some certain packages. And then you see we want to have a very specific Spark version for a very specific Hadoop version. Here it starts what I was saying to you with the real versions, the right versions with the right other versions have to play together, right? And this is something where in MS Azure, you don't have to do these 2 steps. You usually have this already given. You can just assume that's properly installed and the right versions have been there. Here we do quite some effort actually to create this, right? And you see here, we have to then see that we have downloaded this kind of Hadoop Spark distribution. Then we have to basically untar that to, basically have access to it. Then we have to import the operating system environment, set some environment variables. So these are all steps, so to speak, which usually are in the cloud differently. Like MS Azure, you would configure still probably what you want to have by switching to a specific service with some configurations. Like in MS Azure, you would have a template where you steer how many worker nodes and, kind of MS Azure Spark environments you want to have, and many different factors. But there would be usually not so low level as here, where we really install the software ourselves. There, the basically idea of Spark is already installed. And then you go the same way. So you use a step 3 Jupyter notebooks now then to start with this so-called PySpark kernel. So This enables us to do basically Python on the Spark classes, on the Spark software. Again, in lecture 3, we'll talk much more about what it entails. It has also strong library for graphs, for machine learning, etc. We will come to that. But here is basically the idea now to connect the Spark session really to the idea of the, let's say, IPython notebook that I have here, or the Jupyter here inside the Colab environment, to get access to the Spark functionality, right, in order to work with it. And it's basically something where we have, let's say, a couple of configurations which are not so important right now to get then access to the Spark session, which is then really the opener for us to do machine learning, as we will see in this next subsequent slides. By do this, of course, we also not only prepare the environment with Jupyter and the Spark cluster and so on with this, we also have to upload the dataset or get access to the dataset. So here you would have, let's say, the bank CSV file, comma, separated value files. You see it's 70.21 gigabyte that is available. So you can actually ensure that usually you have quite some space in the cloud left to transfer some data. It's a bit tricky sometimes to access it, to know where exactly the data now is. That's why it makes sense to look in the file browser all the time. Here, basically, you can upload the file. I would just say your lessons learned. It's basically better to do drag and drop per mouse than using the upload function for some point of view from my practice and experience in Colab, especially if it's larger data sets. But this is just a short lessons learned. The functionality should be the same. And then we come back to our CRISP. So we basically now what we want to do, we have understand the business understanding of the bank deposit idea using previous customers. You know, they would probably have different jobs, different personalities. And when a new kind of customer comes, we can, you know, already predict, will he do a deposit or not? Then the data understanding is something we have to look now. Check application data set, right? So our environment is now ready. So we have to do the next step in the CRISP, in the machine learning, so to speak, towards the machine learning, I should rather say, to see what data do we really have. And here you see in the Spark session, using that, we can really basically use a bank CSV then to look at the schema. So what data do we have about these personalities? We see we have age, job, married, not married, the balance of the, you know, of the house, loans, etc., etc., etc. So you see lots of information the bank can use now to create an interesting machine learning model out of this. And also connecting to our practical lecture 0.1, you see how nicely it is, again, that pandas is usually used. Here we take from the kind of data frame we would get out here of the Spark reading the bank CSV data part. We can use pandas also to work with these data frames here that come from Spark nicely. And let's say, make them a little bit here as an example, just taking the first 5 here as an example to show. And they work really nicely together. Pandas, as I was alluding to also in the 0.1 lecture. And of course, for us, it would be also good to know if there is, let's say, then this guiding output Y, right? So where is that? The deposit, yes or no? You see deposit, yes, 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 yes. So here in this example, we would have the first 5 customers here that seem to be all those that did a deposit. But of course, the data set is also some which have no deposit. So hence, this would be our X, right? That goes in, our X with the different dimensions here of all the different data, our X vector, not only sepal width, sepal length. Now we have job, martial, education, etc., etc. And our guiding Y that did previously, you know, our historical data, the deposit or not, is basically here. So again, we have our binary classification set up as we want to. Of course, we basically here and there can do more application data set inspection and exploration. In terms of the CRISP, we can look maybe of seeing is a real class balance given. So if you want to take the deposit where I said it was all yes in this first 5, it makes you a bit maybe cautious and things. Are they actually all of them say yes to the deposit? And you see here with a nice data frame group by method, you can actually then check if there's a real class balance existing, which means there's not only, let's say, all of them say yes and just 3 say no. You see, it's fairly balanced from this around 11,000 people that, half of them say no, half of them say yes, a few more say no, but this is not so dramatic. It's still a relatively good class balance. What you should check usually doing classification, especially binary classification, otherwise you tend to learn into one direction if the class unbalance is given. This is important. What we often also do is summary statistics of some point, in some form. We have minimum, maximum values, standard deviations, and so on. You want to know the number of data sets, the mean, and so on. Also to check if there may be missing values, if there's noise in the data, something we can't really work with. This requires really, I think, a whole machine learning session usually to look into it, where you have to be careful sometimes. So here we assume the data set is, let's say, fairly okay. And let's say from Kaggle already prepared in a manner that really helps. Then you would say still in the data understanding / data preparation phase, we're going now this kind of arrow. We maybe want to do, and think about maybe feature selection would be helpful, right? We have all of this different data, but basically day and month columns seems to be not really useful. So we maybe remove them. And then we would say feature selection on the data set could be basically of saying we keep all of them, yes, but we remove the day and months. In other words, we pick the features which are not those two. So in this sense, you already prepare a little bit the modeling, right? You say which features are relevant, which maybe are not so relevant for our machine learning model, which is usually called feature selection, feature preparation. If you have really advanced features, you would even call it feature engineering. You have to do and really work on the data to engineer the data a bit. And then basically you have to think about more towards the modeling and think about, okay, what we will have now is that we have all these categorical columns with all this job, education setup and loan and so on. And we have to basically get this data in a bit more mathematical convenience to really learn from that data. And this is something where you can use some functionality of this, PySpark feature sets that you have here, like a one-hot encoder, a string indexer going through all the strings, and then essentially, doing what we've seen as a table, so to speak, really as a one-hot encoded table. If you know a little bit what we discussed also in the lectures before with the one-hot example of this MNIST data set, right? Where we had then, there are also some ideas of doing this at one-hot encoded. This is very similar. Of course, the output is here very important for us. We would say, we call that now basically the label, the deposit, yes and no. If you remember, we call that a new kind of feature. If you want, it's not really a feature, it's a label really of the data. There's Y. And then here we provide now the features with, age, balance, duration. And then we have some, let's say, other features that we have basically assembled together, basically coming out of our ideas before. So here we do a data preparation already to really merge different columns into a vector column to make it more mathematical convenient for the algorithms. And this entails this data preparation phase. Hence, we cannot just throw this data, which we have seen with the macho status and so on, just to this data, to this algorithm of, linear regression or logistic regression, whatever we pick later. But here we have to really look at the data and do different ideas how to prepare the data, which is this one-hot encoding, for example, or this vector assembler. The beauty is, however, that PySpark environments and, with the help of pandas, with the help of data frames and so on here and there, it's really nicely often done. We also come to a more aspect called pipelines, where then this concept is even better rolled out when it comes to modeling, using these features again and again for different parts of the machine learning pipeline, where we talk about training, testing, possibly validation, and so on. These are all different topics which a machine learning course, of course, can teach you much more in detail. But here you will basically get a relatively moderate introduction into that. So hence we basically still do not really modeling here. We do still data preparation of thinking we have this different labels and features that we just crafted, right? Which was our feature selection, so selected columns with the Y and the X. And basically, if you print the schema, it's looking, let's say, a little bit more harmonized now for us. We have this label, which is important for us, but then also different features in the data set that we have and crafted out of, let's say, our feature selection process, right? And of course, there's still many different others left here, but the pipeline now has different stages. And what we want to do is to fit basically this, pipeline model and transform it using basically our different, label and features. So in the end, we prepare for the machine learning essentially to really make a workflow out of it, as we call that. Basically, it's a typical data science approach, creating data science pipelines for data analysis to change their different aspects in it. And here's the idea is to have different, transformers chained together and so on, that when you have new data, you can always use the same pipeline, so to speak, to really, basically look at this and look at this again and again with different data sets, and still don't have to redo everything from scratch. It will follow the same pipeline, the same transformations, and also the estimators, I should say, which then comes already towards the learning. So here we are heavily in this back and forth already of thinking, okay, we have to prepare the modeling, what we have to do in terms of the data preparation. Hence, we have a feature vector created, for instance, to give the modeling more, let's say, robust features, very condensed features if you want, and of course, a guiding label Y. Now, print this to get an understanding to this, I think is very important. You see here the label still, it's very important of saying is our Y, as you know by now, by heart. We have this condensed features now as a hot, one hot encoded idea here. And this is just the first 5 of these persons, right? And of course, although we have been in data preparation, you still now do the data understanding, so to speak. You just print it out to make yourself know, okay, I'm ready for machine learning right now. This looks good. I can stick it now, basically this data frame or this pandas data frame here into a machine learning model, and will do something when I pick the right columns. And this is, of course, important and brings us to the real first idea of modeling. So now the interesting stuff is with it is still related to data preparation a little bit, of saying when we train on the data set in the modeling, we want to do this on a training set. So me as a machine learner, I need to cut the data that I have in 2 different parts, training and test set, right? That you have from you available. There's no really a guarantee how you do it best, 70-30 and so on. It really depends a little bit on your data. But you see here, we basically differentiate here 70-30% the data into training and test. And then I use my PySpark environment here for using it maybe with a logistic regression modeling in the modeling phase now, really with the idea basically of using then, of course, the train data set. And that's where the fit comes in and where the computing now starts. Because basically what we do here is now the real machine learning will start, the optimization inherently will start to do the modeling of this logistic regression model. You have some parameters. You see input, you give the features. You have the label column is a label, which gives us a Y. And then the max iteration is 10 times. It will try to fit, basically going through the data again and again to fit basically to the training data. Hence, this was a process of modeling that we have done. And then in the evaluation part, you can maybe print out some aspects. You see here the beta coefficients, basically that you have here given your label, and do some other visualization basically on the matplotlib. There are very different ones that you will use usually to evaluate now your model. Is it really good? And of course, we have done this now. It's a mathematical model, so we know the beta coefficients. That's great. But then there should be another process, of course, to evaluating this model on the test set, where we will come to. Just to summarize a little bit what we now have done in this fit function, right, is we were going to this logistic regression model. So instead of just, doing the sine function that we have done in the linear classification, In the logistic regression, we have learned from the video, we squash everything into probabilities from 0 to 1. And basically, we have a pointwise error measure here that we can always check with the error that we have combined basically with our outputs y. And with this, we do 10 iterations and updates of the weights according to this with a specific gradient descent techniques and optimization technique that will now help us to minimize the error based on this error function using the labels we have by doing a so-called optimization step. And this gradient descent is then basically inside the modeling. It's a training of it using optimization techniques by basically reducing the error. So we're still working on finding the right W's and want to update the W's. And how it usually works is that you take the derivative of the function that we have right now. Basically by this, you get, of course, then an ascent, and we basically take a minus of this basically step and subtract the gradient in order to do it a gradient descent to basically lower here yourself step by step to the lowest point. Now, admittedly, that could be a local minima of the function. So this is basically something where the learning rate comes in, which you can steer basically by how quickly you go downhill here, or basically how quickly you jump. But this is a very established learning algorithm, so to speak, inherently is part of this logistic regression. You kind of try to get the error smaller and smaller, but you see here step by step, and update the weights basically always step by step in these iterations, going through all the data again and again and again. And by iteratively doing so, even if the data is not linearly separable, you will down and knock down the error. And by this, you basically learn from the function. You see that a little bit here elaborated basically by different ways how you find now the minimum. You will basically, like this dot here, find your way downhill the error space. A little bit like sitting on a kind of mountain, touching around yourself, and you see, I want to go downhill the mountain. So I touch myself around me and see, touch here and there and see, I have to go to the left. This is the lowest point. And I will do then to the right, because this seems to be the lowest point. You go step by step as a very iterative, elaborate process, of course, downhill. Now, the learning rates is something which could help you there if you maybe just touch around yourself, or you basically hop around yourself if you want, right, to make it faster, jump. But yeah, chances are that you maybe jump too much and then basically not really find the minimum quickly, or basically you jump, let's say, too little, and then you get stuck in a local minima. So all of these parts are part of this optimization part, which I think in a machine learning course, you would have probably 2 to 3 lectures just on optimization techniques, like gradient descent. There are several others which put the velocity, momentum, and many other aspects into it these days, and we will review some in later parts of the course. But by doing this iteratively, you see that basically the loss goes down, and the point, slowly here works more and more from starting up here to go to the very black part here down there into the minimum. And this is where basically taking the derivative and updating the weight vectors and everything, this is a computational heavy step here, right? Which again and again needs to be iterative. Hence, the fit function is something where usually the computing quite starts and where the Spark cluster is needed. In terms of looking then in the evaluation, are we happy with the logistic regression? There are different evaluation models that you can also, I think, better really understand if you do it yourself a little bit in the assignments. One very famous one is the ROC curve that you see can also nicely plotted here. So the bigger, let's say, the area under the ROC curve is, the better is your model. You see here the training set accuracy is 0.88. So that's an interesting training summary, which is important to see. There's precision and recall that you can use basically with this particular ideas here. So long story short, the evaluational model is very important, especially if a multi-class setup. Is every class really very well classified? In a binary classification, of course, that's also already important. But if you have a multi-class classification of 40 classes, 70 classes or whatever, and then your accuracy is like 90%, you would say, well, that sounds great. But then you look into this with the evaluations and see, well, there are always, let's say, 10 to 20 classes that are never correctly classified. So you have to balance this. That's really a good code. Just because the accuracy is very nice doesn't mean that all the classes are very nicely, basically classified. And this is all something which a machine learning course can, of course, put you much more, in context, in perspective, has much more time for this. We also have to go ahead here with cloud computing and so on. Just take away the message that evaluation is important. And evaluation, of course, should be then also thinking about the test set, right? So the test set is data that you don't really touch yet. So here the idea is to maybe using the predictions now on the test set, using the model on the test set, basically using this again, and you see what's coming out by using here the test set that has been not seen before by the training, and gives you probably good insights to each of the different persons. You see here the label, and the prediction is sometimes not really accurate, but in the most of the cases, it seems to be accurate with a certain probability attached to it, which is also kind of helping us very nicely. Will this people, deposit or not? And yeah, so there's this test set that we already did. We can do again the area under the ROC curve to see on the test set now, right, which is important for us. Also, the test was running very well with 0.88. I think that's quite okay for a binary classifier for this interesting data set. So here we're good. So we don't really need to know maybe something about neural networks or support vector machines. Maybe they get a better modeling accuracy, a better area under the ROC curve. So of course, there are no limits. You have time, you go for it. And basically computing power is there maybe as well. You maybe switch to support vector machines, neural networks, or so forth. Right. Always think about that there are different ways also in machine learning. We call that, model selection. In other words, the validation of the model with different parameters, which can be also quite computational aspect, or a computationally loaded. The different parameters, we call that hyperparameter optimization. And that's where cloud computing also comes in. Here's an example of a cross-validator that you also will do in your assignment. So I don't need to talk so much about it, but take away that here basically with a 10-fold or 5-fold cross-validation, we train on 4 and check out, basically have then the 5th for a validation part. And we do this again and again with a systematic way going through all these different parameters. And by having this different, regularization parameters or iterations and all these different parameters checked properly, you spend a lot of computing time, but this gives you a very good model in the end. Hence, here cloud computing also can help you instead of using hours and hours on your laptop to just do it quickly on the computer, on the cloud computing. But yeah, this is things which also will come in your assignment. So I stop here by describing too much. And I think some of these things are better explored on, especially if you change regularization parameter. Regularization is a very important topic in machine learning, which kind of sets apart the beginners from the experts. So the topic really needs to be talked about. I talk about a bit briefly about it, I think in subsequent lectures, but of course a machine learning course can do this much more in depth. I want to finish today to show you another, short, indicator of a service in the cloud that also does machine learning slightly different we have seen, but still, you have to pay the price for it by swiping your credit card.
Traditional machine learning development is a complex, iterative process. Amazon SageMaker Studio solves this challenge by providing all the tools needed to build, train, and deploy models. Let's see how it comes together with an easy-to-follow example. We're going to create a machine learning model to predict the cost of homes in the US. The model uses historical housing price data, number of rooms, and mortgage rates to predict sale prices. All this data can be put into a CSV file and then dropped into an Amazon S3 bucket. With just a few clicks, you can launch Amazon SageMaker Autopilot and spin up models with different algorithms, datasets, and parameters. Autopilot iteratively trains dozens of models at once and then puts the best sets on a leaderboard ranked by accuracy. You can dive into any of these individual models and inspect their features, and then deploy the best one for your use case with a single click. After deployment, you can oversee model quality using Amazon SageMaker Model Monitor. At any point, if problems are detected, you will receive an alert so you can retrain the model as needed. With Amazon SageMaker Studio, you can pull the tools used in traditional software development, such as debuggers and profilers, into a single pane of glass to build, train, and deploy machine learning models at scale. Get started today.
And here comes a disclaimer that I'm, of course, not paid by Amazon. I just want to give you another sort of service example in the cloud that we will also review in later lectures, a software as a service. The references of today, but I think if you look into Kaggle a little bit and, already in the Google Colaboratory a little bit, I think that would be very good also for the preparation of your assignment. We stop here for lecture 2 and we'll continue next week with lecture 3. See you then.